or you want me to take up a particular topic. So a suggestion from Binta is that could we try TensorBoard again? Sure, sure. All right, all right. So let me just go over quickly, like what all we have discussed. So as part of TensorFlow, what we understood is that first, it has a way of it is basically designed to do lazy computation in the sense that it creates a graph and then it does the evaluation later. There are multiple advantages of this approach. First advantage is the parallel computing. Second advantage is instead of having the multiple hops to between the languages, it just does one hop. The Okay, so then there are high level libraries and there are various features of TensorFlow that we talked about. Afterwards, we talked about how to create a graph, and this is how we created the graph. We talked briefly about what is a variable, and then how to create a graph, and then we talked about node values, and we talked about something called session. Okay, so then we did the linear regression example with using a very basic example, and using multiple techniques, but just and then we did the same thing using the TensorFlow. Okay, so all right, so then we implemented gradient descent using the TensorFlow, and then we talked about auto differentiation, and basically the auto differentiation is something that is going to be of use today as well. All right, so okay, then we in the last session we talked about that gradient computation is automated in case of TensorFlow. It provides you gradient function, and it further provides you the functions for the various optimizers, so that you don't have to apply the formula exactly for either gradient descent or say momentum optimizer. So it provides you that out of the box. Then we talked about something called a placeholder. Placeholder is something that we use for our data, as in because that's the one that we feed from outside while running the graph. Then then we talked about how to save and restore models, because saving and restoring is important, either because it takes long time to train something, and therefore something might break in between. The machine could shut down, there could be other problems, and therefore it is better to just resume from where you left off instead of starting from the beginning. And other than that, sometimes you have a web server where you want to do the predictions while you want to do the training on an internal computer. So what you do generally is you create an internal high high configuration system which you do the training, and once you generate the model, you save it and transfer it to the machine where it is supposed to run, say a web server, and there you can load the model and utilize it. So there are many advantages and use cases of save and restore. So these are the basic functionalities of TensorFlow, which we are going to use as we go ahead. All right, and then we talked about visualizing the graph and training curves using the TensorBoard. So the idea is very simple. All we're going to do is we're going to start our, so here okay, let me just give you a brief from the beginning. So So tensorboard helps us visualizing the overall process because print is not going to help much. So tensorboard is basically web application which provides you a nice interface, and it makes it easy for understanding the graph. So what we have to do is we have to create a directory, log directory, in which we are going to feed all our logs, and tensorboard is going to pick the data from that logs directory. Okay, so it's basically going to read the data from the files, and in the files we have to push the data from our code. Okay, that's the main idea. So TensorBoard comes up with a server which you will have to start and then access from the browser. So all right. So one way is to visualize things inside Jupyter, but that is little too not so smooth, because what it does is this approach, the one that you see, that this approach here. Let me start my okay. Let me start my Jupyter notebook. Okay, you need to pull, in case you don't have yet pulled again, you should need to pull the folder and you will get the latest latest project. So here you will see there's a folder called machine learning. Okay, inside ML there is a deep learning, and there is this and this. These are the two notebooks that we're going to use today. So this is the one that we were using till last time. And this is the one that we are going to use today. Okay, so you need to do git pull, and that's it. Let me reload because my terminal is dead. So good. So git pull. All right. And in the TensorFlow one, if you keep going to the end, okay, one way is to visualize the graph from within Jupyter, but this is something I'm not a big fan of. We can instead try something else. Okay, try launching our own server. All right. So all right. So the first step is to make sure in your code that you provide a log directory. So here we are just creating a log directory inside the TF log. First, we are creating TF logs, and inside that one, we are creating one folder for each run. As soon as you execute this, you will get a new string which will be TF logs / run dash the timestamp. So every time you run it, you will have a separate directory for the current logs. The next one is right. Next step is that if we want to, one is that we let the we let TensorBoard gather the graph data, and the other way is we explicitly send some of the information to. So other ways that we send some of the summary information to the TensorBoard. So here we are creating a scalar variable, and we are pushing that. All right. So here basically we are adding the following code at the very end of the construction page in our code, and we will show you that. And once we are done with writing the log, you see that? So here we are writing the log, the graph to the right to this directory, the one that we created earlier. Then we'll be able to visualize it. Okay, so let's go back to the, okay, here using tensorboard, you can execute this part, or let me just run everything from the beginning. So I'll say run all above. Okay, so is it still executing? Looks like that it is still executing. Great. So yes, it finished and it's low. Okay. So here we are resetting the graph. Then we are just defining a log directory variable. This log directory is, okay, let me just show you. So log directory here means it's a string of this format. So every time you run it, you will get a different folder. Okay. Now, in the next step, what we are going to do is we are going to right, do our usual gradient descent, and at this point of time, we are saving some extra variables um, as part of the as part of our graph. So we are saying file writer log directory, and then we are passing the default graph. Okay. And also here at this point, we are also creating one more node in the graph for MSC and so on. Okay, let me just show you this, and then it'll make more sense. Then again, we are just completing the rest of the process here. Okay, and we are saying close the file writer. All right. So also we are adding more summary items at various points other than the usual graph. This helps us in looking at various values in a clear format. Okay. So once this is done, then what we need to do is, okay, once this is done, what we need to do is we need to launch, we need to start the TensorBoard server. Okay. The way we do is the way we start the TensorBoard server is one, we go to the console. Okay, if you are not in the usual console, uh, okay, so here also you could do source activate Py36 just to be sure that you are using Python 3 environment, and then we say go to ML folder. Okay, good. Then we are saying that, okay, we are saying tensorboard log directory, and this one we are saying in my home directory, this still there you see here in my home directory, I have checked out ML folder, and then inside that there is deep learning, and inside that there is tflogs. Why? Because here since this file tensorflow.ipnb is inside deep learning folder, therefore when we are creating anything relative with the relative naming here, it's going to be inside deep learning, or after that it is going to be relative to this home folder of this file. Okay, and the home folder of this file is uh, deep deep underscore learning, and therefore the folder that we are mentioning here, this one, okay, this one here, is going to be created with respect to the current folder of this notebook. Okay, so we are saying in my home directory there is ML, there is deep learning, and inside that we have created a folder called tflogs. Okay, and here we are mentioning the port explicitly. Okay, sometimes if this is busy, a port is in use, then you might have to give it a bit of try. You might have to try other ports like 6007, 6008, and so on. Okay, so once you have executed these steps, right, you should you should launch the TensorBoard from the console. So let's try to do that. Okay, so in the console, please execute these. Okay. All right. Are you able to uh, open the console or the terminal? There are multiple ways of opening the console. One is you go here in the Jupyter and say new terminal, or you go to my lab and there you click on web console, or you do SSH. Okay. Or you do SSH. All right. So let's just launch it. Okay. So this domain name that you see here, okay, you should replace it with the domain name that you see here in the terminal at the top, because this one is local to the terminal, and this one is something that you are accessing it from the uh, i- from the network. So you should use e.cloudxlab.com. Okay. If it is f.cloudxlab.com, you should use that one. Okay. So basically, this is the domain name which is public for this terminal. Okay. So let me just try to do that. Okay. So this is my domain name. Yes. Are you able to start? Bintao, Gigi, James, Shiva, and Shahrukh. All right. Let me explain again. So here, first of all, we created a folder. So every time we'll run it, we will get a new folder. Okay. Every time we run it, we'll get new folder. Second, we created a file writer and we started logging the default graph. We started with the default graph, and then we are adding more summary items to the file writer. All right. And once you're done, then you launch the TensorBoard. Launch the TensorBoard, and to launch the TensorBoard, you'll have to first of all activate the Python 3 environment. Second is step is no longer required. Okay, this step is no longer required. You can simply okay. Let me just also change. Okay, so this is the port that okay. So activate the Python 3 environment, then you launch the TensorBoard. You need to change this port number, and the folder name is going to be similar if you have checked out at the similar location. Okay, and once you're done, then take this URL, or you just take the host name, whatever is your host name. Is it e.cloudxlab, f.cloudxlab, or g.cloudxlab? It would be either of those three, then followed by the port number. Okay, so then you'll be able to see the TensorFlow dashboard. All right. All right, these are the old runs which we did last time. We can hide them. This is the run that we did today. Okay, and So here, those summary variables that you have added, those are the ones that appear here, okay, while the graphs appear in the graphs tab. All right, let it load for, I think it's taking some time to load. Okay, I'll just use today's one. Yeah, this is the one. So you can see that this is the graph that we're going to use. Okay, that this is a graph that is generated. So you can see. Should I explain the graph? Okay. So should I explain the graph? Okay, so let me zoom it a bit. Okay. All right. So here you see thetas, right? Initially, the thetas are randomly uniform created, as in they're created in a random fashion. So let's just go up a bit. So you see, the theta in the beginning are basically the random variables, right? Random variables. Okay. Then, then so basically, this is what we want to find out, and we start with the random variables here. Then using these thetas, we do the random predictions. Okay, predictions, not random prediction. These are predictions. Okay, so predictions depend upon theta and and the x, right? The x. Okay, so do you see there are two arrows coming in? There are two arrows coming in till the prediction. Predictions are a function of x and theta, right? The next step is uh, to compute basically the gradients, okay? And how do you compute the gradients? Based on the predictions, we find the error, right? You see the MSE, this is the error that we have got. The error is square of subtraction of y and the prediction, correct? These are the actual values, these are the predicted values. And this is basically a subtraction of y and predictions. Then we square it, and that is the mean square error. Okay, this is the another summary item we had created. Now, using the square, we compute the gradients. Okay, we compute the gradients, and using the gradients, we compute the using the gradient descent, we compute the various theta. So that's what is going on here. All right. I hope this is clear to you. All right. So does it make sense to you? So we start with here we started with the random variables for theta, and then we computed the predictions. And the predictions are computed using two things. One is capital X and theta. Multiply these two, and then we subtracted the actual versus this. That's why you have two arrows coming in from y and prediction. Then we squared this one. For squaring, we just needed one, and then gradients were computed based on this, right? Gradients were computed based on this. So let me show you this. Okay. So this is MSE. This is the mean square error that we are talking about. Mean square error. And the gradients, let me go back. Yeah. So the optimizer is basically this part, and it's here we are saying optimizer dot minimize, right? So this is the part that is happening here. Okay, so that's pretty much. And right, there, yeah. All right. So basically, this is the graph that represents our current flow. We can also do a couple of more things further, and then come back again and take a look at the graph. Say, for example, if let's say we are here, and say in the beginning itself, and let's say we are creating this graph. So we'll have to do file writer. Wait. We will have to go back and yeah, this is where it was. So we'll just save the graph and that should be good enough. Okay, so this is the file writing step. And here we are closing it. And here we are initializing it. Okay, so this is what let me try to do with some other simpler graphs, so that will make you more comfortable with the graph. Okay. All right. So here, let's say we are defining an extremely simple graph. Let's say this one. So here we are saying, as in initialize the file names. Okay. Then once we have created our graph, then we are calling it, calling the, okay, calling the file writer and saving the default graph. And once we are done, we are closing the file where we are writing logs. All right, now let's take a look at okay, should we reload it? So this is the one that is probably the newer one. So you can see this one. Yes. So yeah. So here we are basically doing very simple thing. We're multiplying x with itself, correct? X with itself. Then we are multiplying x, this value which we computed with y, right? And then we are at this point we are also adding this with this. So this is exactly what it means by this expression. So where was the okay, yeah, right? So we are computing x. First we did x into x, right? We did x into x, x into x. This is the place where we are doing x into x. Okay, and then we are saying x into x into y, right? X into y, correct? And then we are basically doing x into y, and then at the next step we are adding the two values here. We are saying further add it with y, and then we are, yeah, this is where probably we are also adding 2 here at this point. Okay, and then I think this is where we are adding 2. Okay, yeah, so I hope this is clear to you. So TF logs is a folder where we are saving the data, right? We just created a TF logs folder. It is inside. It is inside the folder where our tensorflow.ipnb is kept, right? So we have just created a folder called TF logs. Okay, does it make sense to you? Binta, was I able to answer your question? All right, is everybody able to do this part? So every time we run it, we are going to get our own folder. And that's why we basically created the folder name based on the current time. Inside tflogs, we are creating a folder with the prefix run and the current time. And that's what you see here. You see, these are the folders that are being created. And we're launching the tensorboard with the tflog folder so that it can discover the logs that we are creating. Okay, since it has no summary item new one, therefore there'll be nothing in this. All right, so you can see clearly that we were able to draw our own graph, and as the complexity arises, we should be able to load our graph and look at the graph and debug what's going on there. All right. So great. So we were able to create a new custom graph for our kind of work. Okay, and is it happening here also? Okay. Oh, this is actually very clumsy. Okay. This is the one there where we are displaying the TensorFlow inside the notebook. This is not very stable. It's not very stable. Okay, but nothing to worry on. This is useful only when we don't have access to the console and we can't launch the TensorBoard. But in our case, we are able to launch the TensorBoard ourselves, and hence it's completely okay. And we are able to access the new tensor, the new uh, we are able to access the TensorBoard server from the browser in the new window. All right, so this was a quick example of how to use TensorBoard. And please make sure, all of you, that you give it a shot, you try by yourself, because this is going to be used very often as we go ahead. Okay, this is going to be used very often as we go ahead. All right, so that was TensorBoard. Should we move ahead to the next topic that we were discussing last time? So as the complexity of graphs arises, right? So mm, we end up having just too many variables. The graph will be too much cluttered with thousands of nodes. And we can avoid this by creating something called name scopes. Okay? So all we need to do is we need to provide a name of this. Okay, so I'll show you here. So basically, whenever we are defining a variable normally, it is in the default namespace. And whenever we are creating a name which is already created earlier, TensorFlow puts a suffix to it. Okay, _2, _3, _1, and so on. And and basically that's how your namespace or your names of variables basically become cluttered, right? Now let's take a look at it. So to avoid this kind of cluttering, what we can do is we can define our own name scope. Like here we are creating a name scope called param. Inside this, we can have our variables of any names, right? And in case you define another name scope with the same name, it's going to be generated just like earlier. It's going to put _1, _2 after this name. Okay, so here it's going to basically give it a name of param _1, This one will become param underscore 2 and so on. So here, that's what we are trying to demonstrate, that even though the internal variable's name A remains correct, it doesn't get cluttered, but it is inside the this name scope. So whenever we are dealing with our project or our function, we should generally create a name scope, and inside that we can define our own variables, right? So let me just walk you through this. So here, this is what we are doing. We are basically resetting the graph, and then we are saying a1 equals tf dot variable, and then we are providing the name for it. And here also, and once we are done, we are basically printing all of these names. So the actual name for a1 is a2 is a1, and so on, right? For this one, the name of a3 is param slash a, and name of a4 is param underscore 1 slash a. All right. So it just we need to be aware of the naming conventions in case of TensorFlow, because after, when we look at something in the graph, or when we want to debug something, we should be able to clearly see that we are not reusing a certain variables for multiple purposes, right? So that's the objective of namescopes. Now, okay. So for example, let's say for example here, let's say we wanted to take a look at the graph, and we wanted to clearly see that the MSE is under something called a loss. So the mean square error computation, everything we want it to be under the name scope or loss. Okay, and so let's take a look at it. Okay, we go here. Once we run this part, what's going to happen is, here we are basically doing everything exactly same as we did earlier, just that these two lines we are putting under the name scope as loss. So tensorboard would display it distinctively, as in it will create a separate node for loss, and then it will put these two variables under that. Let me just show you this. Okay, go back to the tensorboard and refresh the screen. I'm hoping that all of you are able to run this. Okay, now you see that this loss essentially is representing these two steps. Okay, so you can see that the loss, this node, is coming from here. Okay, where we define the name scope. So this loss is essentially having error and MSE. So this is, you can see that namescope provide a very good abstraction over the complexity. Okay, when you double click it, you will be able to see that inside it there is MSE, there is this piece of computation. Okay, so similarly the gradients, you see inside it what's happening. Okay, now moving ahead. So with namescopes, you can avoid cluttering of variables, as well as you can take a look at the TensorFlow, and there also it would avoid the cluttering of the variables. All right. The next thing that we discussed last time was modularity. Okay. So let us say we want to add the output of two rectified linear units, ReLU. ReLU is extremely simple function. What is ReLU? ReLU is nothing but a normal line, right? Except that there is nothing negative about it. Okay, there is nothing negative about it. So what does it mean? So how do okay, so new sketch window. All right. So here, let me explain. So let's say we have, this is our, right? This is, let's say, our X, this is our Y, and let's say there are two variables. So this is X, this is Y. So generally, this line is, or let me draw a line from here. So, okay, or let me just draw the line. Okay, okay. So let's say there is a line here, right? So this line is generally like y equals some multiple of x plus c, correct? Why are we discussing this? Because ReLU, or rectified linear units, are very useful, and we're going to use them in the in our discussions during the neural networks. So so this is a straight line where y equals mx plus c. The only difference with ReLU is there is no negative part to it. This part is 0. Okay, so this part is 0. So it is like, okay, or actually, I'll put it the other way. Okay, so the rectified linear unit is basically the max of, not this one. Okay, so when this y starts going to 0, then not, okay, so think of it this way actually. Yeah, this is a better way to present it. Okay, so let's say there is a straight line y equals mx plus c, when x is say, so when, let's say, y is x is 0, this would be something like, okay, so y equals mx minus c. Okay, this is some, we're just putting this line now, or you can just say y equals mx plus c. This c is some number. Now, the moment this value starts going to 0, okay, and below, instead of the line continuing like this, under this, it is basically 0. So this is what we call the ReLU, the rectified linear unit. So it's a max of the two, either x multiplied by weight plus bias, okay, or 0. If this is negative, which means it is going to be smaller than 0, therefore the value is going to be 0, otherwise this. Okay, so it's a function that we are going to use to convert our output into something positive. Okay, when we don't want negative numbers in the outcome, we generally use the values, and we will discuss why we use them further. So let us say that as part of the TensorFlow assignment, what we need to do is we need to create multiple values. We want to create multiple rectified rectified linear units, right? Rectified linear units, and we want to create a graph out of them. So you can see that we can, for let's say 1, here first of all we're creating a placeholder for x. We are saying that x is a placeholder with a float 32 data type. The shape is none, and number of features are these many. We are passing 3 as number of features, so it is going to have many rows. None means many rows, and 3 columns. Okay, and we are giving it a name called X. Then we are defining W. W is the weights that we want to find out in general. And here we are creating initially some random values for W, right? Some random values. Again, this one is going to have basically 3 rows equal to the columns of this one, 3 rows and 1 column, right? And these many weights. So, and we are creating a bias variable here with the initial value at 0. So for each of the values here, we are creating 2 values. So for each of the values, we are going to create W, we are going to create B, and then we are going to compute the multiplication of X with W, and add B to it. Okay. Similarly, for the second one, that's what we are doing here. And finally, we are creating the value by saying maximum of either the actual value or 0, right? We're doing this for both of the values. Now, question to all of you is, do you see any problem with this code? So we are creating 2 values, okay, rectified linear units, value 1 and value 2. So do you see any problems with this? Anyone? James, Pratik, Shiva, Shahrukh, Abhinav? So here we are trying to create we are trying to compute value 1 and value 2 given the variables x and xw, given the variables xwb. That's right. That's right. Thank you, James, and Bintao, and Shahrukh and Shiva and Abhinav. Great, great. So basically here we made a mistake. Instead of Z1, it should have been Z2, right? So that's exactly the problem with this kind of a code. Non-modular, the more code you write, the more number of lines you write, the chance of error becomes more, and therefore it's always advisable to shrink the code into modular units. Like in normal programming languages, what we do is we create functions and we reuse those functions instead of typing the code again, right? In the same way, instead of creating these nodes or these variables of TensorFlow in this manner, we could actually define a function like value x, and it would basically create the graph for us and return to us. Okay, so here this is what it is doing. It's basically creating this value x is creating new variables for us and returning the graph. Okay, so that's exactly the objective of functions is. So here you see, all right. So here you see that this ugly graph, we end up making mistake in this, but this one is far more cleaner. Okay, here we are defining. Here we are. What do you say? We are creating a function called ReLU. It's a usual Python function. Then inside it, we are saying that we are giving it a name, this scope as name from here to here. It's this everything, all the graphs that get created here would be under the same name scope. And inside the this name scope, we are going to we are going to create these variables W, B, and Z, And finally, we are going to load this. Now, before you run this, change this to tf underscore logs so that it gets created in the same folder. Okay, it gets created in the same folder so that we can visualize it in the graph. Okay, so change this to tf underscore logs. All right. A very good question from Bintao. Question is, how do I unit test such functions? Yes. So for unit testing, you can actually, yeah, that's a very good question. So you can do exactly the way we do the unit testing. Now, for some of you in the session, unit testing could be a new term. Okay. So in most of the programming, what we do is we make our code modular and we call them units. A unit could be mostly the unit is generally the smallest unit is as the function, a function. Sometimes a unit is also like a class. So what we do is for every logical unit which is doing something, we create a test function parallelly, and we create various test cases for each function. We give it some input value and compare with a previously manually computed output or expected output, and then see whether it's working or not working. So just like with Python using asserts, we can call this method, okay, and maybe we'll have to write our own wrappers along with this. And then, so these parts is what we need to do here. Whatever we are doing as part of here, while we are evaluating, then we'll have to run this. Okay, it's a good question. It's a good question. I think I would rather create example code for you. Okay, let me just save it as notes for myself. Okay, 31st March. Okay, and deal. Good question. So what I'll do is I will actually create some kind of test cases which you could do. Okay, generally, let me just show you. Let's say this is my program. Okay, what it does is let's say whatever you pass is it as argument, you return say x into x, okay, x square. So generally the way we test this is we create assert functions, we call my program with some value say 3 and compare the result with 9. Okay, similarly we create multiple test cases, right? So these are called test cases. So this is how we generally test our application. Okay, we say assert equals, and okay, I'm not sure which libraries we would use for Python with this. Okay, so well, let me do this actually. Let me do this. I will try to create more meaningful example. Okay, so in general thumb rule is going to be that we have to create our own asset functions, and we'll have to initialize session, and then inside the session we will run these and evaluate whether the outcome is matching or not matching. All right, so good. So we are going to do that probably. The only important part would be that how to create the session such that it's valid for all the test cases. So we will do that. All right. So that's the to do. Create an example of Python TensorFlow unit tests. All right. Good. Very good set of questions. Okay. A question from Minta is, could we have such a project to practice the unit tests? Sure, sure. We would do that. Okay. So unit tests are more popular in the cases where we are doing a lot of data cleaning, data uh, data churning, or any other logical work. Wherever there is a lot of logic is involved, it's very important to just let the system check it. Say somebody else comes up and they implement their own function here, right? And instead of you checking it next time, these two lines of code will check whether my program is still performing as by itself, or working well, or something has gone wrong. So generally, this test cases, the one that we're talking about, they become the part of the deployment, or part of the something called basically the staging area. So as soon as somebody is committing, so when the user is committing the code or making some changes, automatically the test cases are run on the staging area. The new code is pulled, the test cases are run, and the report goes to the team. Okay, and that's how the larger projects are maintained in industry. So let's see if I could do an example of TensorFlow in the same way. Okay, though it's going to be pretty simple, as in we're going to initialize a session, call it with the existing values, and so on. All right, so that's what we will do after this. All right, so what we can do in case of TensorFlow is that instead of rewriting the code to create the graph again and again, we can use the function to create the graph. So let's say here, this is the graph. So here it's going to create this graph in the file, in the directory tflogs/value. Okay, so we just did that. Let me refresh it. I'm hoping that, okay, let me refresh it. Okay, so here is the folder that we just created. Okay, so do you see that? So you see, so the output is ReLU, ReLU1, ReLU2, ReLU3, ReLU4. You see that? So it's so nicely abstracted from us. Okay, right? So here what we have done is we have defined the function value, given it a name. Okay, this oh, all right. Let me show you the notebook instead of this. Okay, so we have given it a name here. We've given it a name value, and you can see that every time we are going to call this, since the name scope is being repeated, it's going to create new name scope called ReLU1, ReLU2, ReLU3, and so on. Okay, and right, so this piece of code is abstracted inside the value. So here this is where we are creating so many values. So we are creating 5 of these, and we are adding it as a part of the array. Okay, so output is basically a bunch of such functions. So you can see output is ReLU, ReLU1, ReLU2, ReLU3, ReLU4, and so on. Okay. Now, inside this, if you double click, you'll see the actual work going on, right? There is, right, weights being assigned as random values. Then there is a multiplication here. Okay, there's a matrix multiplication with the x values which are here, and then so on, right? So that's what is happening. So is everybody able to create this now? All right. So similarly, we'll use the same principles as we go ahead while we are creating our own neural networks. We're going to individual parts, we are going to abstract inside the namescopes. So we have got 5 namescope, and we've got same one variable being passed to all of these, and we got the output. All right. So I hope this makes it very clear what's going on with the graph. Yes. All right. So great. Should I move ahead? Everybody is able to visualize the modularity part, visualize the five value functions. Okay. In case this is not appearing in your here, new one, you need to refresh it. Also make sure that here, this is TF logs. Actually, it was something else. So it should be TF logs. Otherwise, it won't appear because right now this tensorboard is reading the data, reading the logs from this folder because that's what we started with. Here, when we started tensorboard, we said that tensorboard, the log directory is in TF logs, which is inside deep learning, right? Great. Should we move ahead? Okay. So now what we learned just now is if the name already exists, it appends underscore followed by an index. So the first value contains node names as weights. Okay. If you double click the value, it will have weights, biases, Z, and so on, right? Uh, and again, the values for other biases 1, 2, 3, 4, that is part of the weights. The naming convention for the same is like that. Okay, so we have already, yeah, I think we have already seen all of these parts. So if you double click it, you will be able to see that they have their names. Now, since we have defined our values really well, so the internal variables are, are having clean names instead of 1, 2, 3. Okay, you can see. Great. So this was a quick overview. This was a quick overview of modularity. Now, moving ahead with something called sharing variables. Okay, there are many ways to share the variables between the multiple units. Okay, and most of the existing techniques that we have learned with sharing variables in Python, those still apply. Okay, there are just minor tweaks. There are minor tweaks to it, and whatever we are going to discuss now, those are useful, but without knowing these parts, you can still do well with rest of it. Okay, rest of the TensorFlow. So question is, how do we share the variables between the various components? A classical way is to first create the variable, then pass it as a parameter to the function, right? That's how we do. That's how we do. Let's say we have some function fx and we want to use threshold again and again, right? Generally in other programming languages or elsewhere, what we do is we create this public variable or static variable or constant, which is accessible to the entire code. The other cleaner way, one other way was to use the argument just like this, and let's say we want to pass threshold everywhere, so we'll basically put threshold as an argument to all the functions. Now this technique is okay, this is okay if you have only one or two variables to share. Okay, so say for example we have this value function. Instead of cutting off at 0, we are saying that if the value is below certain threshold, return 0, otherwise return 1, right? So instead of cutting off at negative value or 0, so we basically are cutting off at certain threshold. Okay, So so let's say we want to pass this threshold as an argument. So we would create an external variable threshold and we'll pass it to the ReLU function every time we are calling it. Now, this is good enough. This is good enough. The only problem with this is that, let me ask you this. Okay, so this is good enough actually. So the question to all of you is, what is wrong with this approach? Is this approach clear? That what we want is, instead of the ReLU stopping at 0, okay, we want it to stop at a certain threshold. All right. So what does ReLU do? What does ReLU do? The moment the value of y starts going negative, it stops. It doesn't change. So 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 it basically sets it to 0, whatever is negative value. We could do the same thing with, say, certain threshold. Let's say if the value is below 0.5, mark it at 0. Okay, so that's a threshold. So let's say we are defining threshold. One way is we define the threshold and we pass it as argument to ReLU. So my question to all of you is, do you see any problem with this? A question from Bintao is, what is underscore n in tf.add_n? Underscore n. Yeah. So basically we are appending these values into an array. Okay. That's what it is doing. So we are basically just appending this value to the output. Okay. We are not doing any computation. All right. Also as right, if you have, let's take a look at tf.add and question mark. Okay, so you can say it adds all the input tensors element wise, right? The inputs is a list of tensor objects. Each of them has size and shape, same shape and type, and then it returns a tensor of same shape as this. So basically it appends these uh, to the uh, output. That's all. Okay, so that's all it does. Okay. So any suggestions? Do you see any problem with this approach? So we created a threshold variable and we are passing it to this function here. See, because we want to share the threshold variable with all of the functions, right? With all of the values. Any problem do you see with this? Bintao, James, Pavan, Pratik, Shiva. You don't, there's no problem that you see here. Okay. All right. What happens is that if there are many shared variable, okay. Okay. So question from Binta is how to check the output. You can just run it. Okay. And also maybe you can, right? Maybe you can do what we did just now. We can, okay. So we could just write it here. Maybe we'll just say ReLU4 and write it. And then in the TensorFlow, we can reload it. Okay, so like that. Okay, so we have this. So what's happening here? We are okay. How come how come this became the input? That's all okay. Oh, it's actually just the arrangement. Okay. All right. So yes. So here the the challenge is that if there are just too many parameters, then you will have a huge list of arguments that you need to pass every time to the functions, right? And like for example, okay, so a question from James is if thresholds are going to be same for all 5 values, it may as well be declared in the loop instead of being passed. That's right. That's right. So we'll have to maybe create a public variable, maybe make it accessible everywhere, and so on, right? That also we can do. So that also we can do. But what happens if we are passing the variable, if we are having just a normal variable, what happens is the variable being modified or accessed by too many places that it becomes impossible to keep a track of it, right? Thus, if we are passing the variable every time, the downside of that is that if you're passing the variable again and again every time, the downside is that if there are too many variables that you need to pass, then it becomes too clumsy approach. There are just too many arguments that you need to type every time. So one of the ways is that you create a Python dictionary and we pass the dictionary of values. If there are just too many things to pass to a function, that's what we do. We create a Python dictionary and we pass it around. Otherwise, we create a shared variable as an attribute to the ReLU function. So the ReLU function itself can have an attribute, right? And we set that attribute. So here we are setting that attribute. We are saying that if this does not exist, then this. So here there is no, as such, the perfect way of doing it. There are these approaches and we are comparing between the approaches, right? So here what we are doing is we are saying if the ReLU function, every function can also have the attribute, right? So if it doesn't have an attribute, then also this is not the part of the TensorFlow. This is normal Python. So here we are saying that if ReLU has an attribute threshold, then if it doesn't have the attribute, then create the attribute by saying ReLU.threshold equals this. And basically that's how we are going to use it. We are going to access it using ReLU.threshold. So this is one way to do it, right? So TensorFlow offers a cleaner and more modular option using getVariable function, right? So you can create a shared variable. You can create the shared variable if it does not exist or reuse it if it already exists. Okay. So for example, the following code creates a variable named ReLU/threshold. Okay. And so it's going to create the variable, use a shared variable like this, and then we can use that. All right. So this is how you create the threshold. You create a shared variable. And when we are creating shared variable, the challenge again is that every time it's going to try to create a new one. So instead of that, you say that reuse equals to true. So inside a variable scope, so we define something called a variable scope. Inside the variable scope, So remember, earlier we created name scope. Here we are creating variable scope. And inside the variable scope, we are saying, give me a particular variable, right? And if we are going to share a variable, make sure that we say reuse equals to true. If we want the variables to be shared, okay? Or we could say scope.reuse variables. All right, so that's pretty much with respect to reusing the variables. And we could use the variable scope along with the get variable function with reuse equals to true marked. So this way we can at various points we can just say that using this particular scope with this particular variable scope, we are trying to access this particular variable, and then we can set the value, access the value, or do anything with a particular variable. So these are TensorFlow's variables, and they are more efficient than normal sharing of variables in Python. Okay, so so TensorFlow offers a way of sharing a variable or a constant across multiple executions or multiple pieces of code. And the way we do is using the variable scope, and we define a variable's scope, and then we say get variable, and that's how we do that. Okay, so that's what pretty much about TensorFlow that we are going to use as part of this course. These are the main parts to it. Rest we will, in case there are some more ideas, we will learn those as and when we are going ahead. All right. So let's start with the rest of it. So we learned many things about TensorFlow. We learned how to how to create a graph. We learned the various kinds of variables. We learned the gradients. We basically tried to compute the gradients using TensorFlow. We used the optimizers. We used the tensorboard. Learned about placeholders, saving and restoring. We learned about modularity, that we can use the functions of Python to do to create the modular graph. Then we learned about name scopes and then variable scopes. All right, so that's pretty much about the overview of TensorFlow. Okay, now we will go into more details about the neural networks. We will start learning. So far, this was the tooling part of it, where the way, while before starting the machine learning course, we covered the NumPy, SciPy, and other parts. Similarly, before starting the deep learning part, we covered the basics of TensorFlow. Okay, so we are also going to learn how to scale up TensorFlow using multi-threading, queues, and multiple GPUs and multiple servers as we are going ahead. All right, so okay, should we start with the ANN, artificial neural networks? It's going to be some of this part is going to be a bit of theory. Okay, so you need to ask questions in order to stay awake. All right. Should we start with the artificial neural networks, the introduction? Yes. All right. Even if you have missed the TensorFlow introduction, even if you have missed some of the scikit-learn introduction, don't worry. It won't be that difficult. We will learn as and when we get stuck. Okay. All right. All right. So question from James is that should we take a short break first? We'll just take a break after maybe 5-10 minutes. Or if you have more questions, I would love to answer the questions before jumping ahead. So this session is going to be really, really interesting, and we are going to learn something really important. Okay, and this session is something that is going to be kind of sufficient in itself. The sufficient in itself that you will get the complete idea that how does the neural networks work, and the remaining of the chapters would be around the architectures, different variations of same thing as part of this chapter. Okay, and say for example, CNN, RNN, and other kind of networks, they are basically based on the same principle as what we are going to discuss in this chapter. All right, so we're going to go into the basics of neural networks, and then we are going to go into more details about them. All right, so let's start with the basics of the neural network, and then we'll take a break, and then we will continue. All right, or you want to take a break first? All right, so great. So let's start. Great. All right, so we learn to fly by taking inspiration from birds, and even the very simple innovations like Velcro was inspired by the plants, the burdock plants. Burdock plants. So essentially, a lot of innovations of human came from the inspiration from the nature, right? A lot of ideas came, almost every idea in one way or another is inspired from the nature, right? And then it seems logical to look at the brain structure for the inspiration on how to build the intelligence. Okay, so it's not not only the usual way, but a lot of researchers thought, okay, in order to build the intelligence, even though we are able to create programming language, we are able to create computer, but it would be in it would be logical to take a look at how brain functions and try to create an intelligence machine. And that was the key idea behind ANN. That was the key idea behind artificial neural networks. So our brain, uh, basically, the the animal brain is the inspiration for ANN, right? So the artificial neural network are the very core of deep learning, what we are going to learn. They are versatile, powerful, and scalable. And the idea is to tackle large and highly complex tasks. Okay. Say, for example, as of today, the, the, the neural networks are being used in Google Images to search images, classify images, and so on. Similarly, for speech recognition, finding the information in the services like Alexa, Apple Siri, and so on. Similarly, we have the YouTube and they are basically doing video analysis, recommending the videos to people, and so on. So similarly, there was the world champion of Go who was defeated by the program called AlphaGo. AlphaGo was designed based on the neural networks. Okay, so basically, the neural networks have been doing a very good job at 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 the prediction or at the machine learning. So neural networks are able to some extent, display the same amount of intelligence as animals do. Okay, so in this topic, we will cover the introduction to artificial neural network, tour of the first ANN architectures, then we'll talk about multi-layer perceptrons, and then implement one using TensorFlow, and we will do the MNIST, and you will notice that the image recognition is far more superior with neural networks as compared to the normal linear regression. Okay, the one that we did earlier. So here we're going to take up the same problem and we will try to do here. So MNIST is digit classification problem in which we are given the images and the labels that what is there, which digit is there on that image. That label is provided to us, and then what we have to do is we have to learn from it, and then we have to start predicting the digits. That is the objective of MNIST. Okay, so we'll implement that as part of this session. Also, we will cover briefly what is the core of neural networks. The core of neural networks is an algorithm called backpropagation. We're going to give you an overview. If you want, we can have a separate session, not part of a regular session, to basically learn exactly how does the backpropagation works. Okay, backpropagation involves a bit of differential calculus, and though you will get easily without knowing much exact details, but in case if you are interested in specifics, we can have another session in which we'll go into the mathematics of the algorithm behind the neural networks. Okay, so the artificial neural networks, or ANNs, were first introduced long back in 1943 by a neurophysiologist called Warren McCulloch and the mathematician Walter Pitts. In their paper with the title as A Logical Calculus of Ideas Immanent in Nervous Activity, they basically presented the idea about how does the neural networks work. Okay, they presented a model how biological neurons might work together in animal brains to perform complex computations. This was the first artificial neural network architecture. Since then, many other architectures have been invented. The early successes of ANNs until 1960s led to the belief that we would soon be conversing with intelligence machines. But due to various reasons that we will talk about, due to various reasons like insufficient computing and so on, the funding of artificial neural networks or this domain took a hit, as in basically people did not believe that it could actually happen anytime soon. Okay, so ANNs entered a long dark era in the sense that the funding went elsewhere. People stopped focusing on ANNs, and the alternative techniques like SVMs were performing well. So basically, people did not focus on the ANNs. Now, in early 90s, there were a revival of the interest in ANNs as new network architectures were invented and better training techniques were developed. So there was a revival of the interest in ANNs, but by 1990s, powerful alternative solutions for machine learning were available, such as, say, support vector machines were favored by most researchers as opposed to the neural networks because they were giving the better results, and they had a stronger theoretical foundation. It was possible to prove that, yes, this will give us great results in case of SVMs. In case of the neural networks, it wasn't giving great results because of various reasons, as well as it was not possible to prove that it will actually work. Now, why ANNs are relevant today? The important part is today the data is available. Huge quantity of data is available to train neural networks. Second, the ANNs have actually frequently outperformed any other machine learning technique. And they are able to handle very large and complex problems. There is a tremendous increase in computing power, which makes it possible to train large neural networks. So this is the main reason. This is the main reason why first and last are the main reason why the ANNs have come back. The data is available and the computing is available. The computing as of today, you have these powerful GPU machines. What are GPU machines? GPU machines are nothing but many CPU cores packed on the same chip. Those are called GPU card. GPU cards were designed for gaming industry. Gaming industry people used to have these graphical units, and the purpose in case of gaming industry was that since in gaming there are a lot of computations required, lot of matrix multiplications are required. Therefore, what they did was they created a separate processors just for doing the graphical computation. And since graphics also involves matrix multiplication, algebra, the differential calculus and everything, so it was very logical, it was very sensible to understand that the whatever graphical card we are using, the graphics card, or we call it GPGPU, general purpose graphical processing units. So whatever GPU we are using, the same could be used in machine learning, because you have seen by now that when we do X into weights, we are actually doing matrix multiplication. Whenever we are trying to solve an equation or a concurrent set of equations, we are doing the matrix operations, which are same as what happens in case of gaming. Therefore, the same computing power was now available to ANNs, and that led to a lot of innovations, because it was possible to uh, do something in a day which was not possible earlier in couple of years. Okay, therefore a lot of hypotheses were quickly tested and we got the results. So that's why ANNs are relevant today. So Warren McCulloch and Walter Pitts proposed a very simple model of biological neuron known as artificial neuron. It was basically kind of on and off, kind of a switch. The idea was that the inputs and outputs to the neuron are are binary. Okay, so the thought was very clear at that point of time as well, that individual neuron is essentially a very dumb unit. Basically, it takes some input, gives out some output, and all of these neurons are connected to form certain kind of structure. And so the only difference was the thought that individual neuron will basically have binary inputs and multiple inputs, binary on and off, and a single output. So okay, so just like we have Boolean algebra in the same way. So the artificial neuron simply activates if the output its output when more than a certain number of its inputs are active. Okay, and So that was the design, the first design of artificial neuron. So let's build a few artificial neurons with that thought that perform various logical operations. And here we'll assume that a neuron is activated. Let's say there is a neuron. Let's say the definition is when two of its inputs are active, then the neurons become active, right? The output, it gives an output if the two of it are active. So the C equals A. This is the case where A, both the inputs to the C is the outputs of A. Okay, that's the so here if A is activated, then neuron C gets activated as well. It receives two input signals from neuron A. But if A is off, C is off as well. So this is basically the very simple example of C equals A. Doesn't make much sense? Yes, but but let's take a couple of more examples, then you will get a fair idea. So the second one was the second, let's say we want to build another kind of structure where there are two neurons connected A and B to C. First input is coming from A and second input is coming from B. And here the the idea is that C will get activated when at least two inputs are active. At least two inputs are active. So here, when both A and B are inputs, since A and B are inputs, so when both of these are on, then C will give the output as on, right? Because C gets activated only if there are at least two inputs. Okay, at least two inputs. If there are more than two inputs, then also it gives one. So it's an extremely simplified model where all it is doing is in case the number of inputs are greater than two or equal to two, then it gives output. Otherwise, it doesn't give output, right? So here A and B was this simple connection. The third one was, let's say we want to do A or B. So this is how it's connected. So there are two inputs to C going from A and two inputs to C going from B. Therefore, if B is off, the input to C will be A. If if A is off, then inputs to C will be from B. If neither A or B is available, then there will be no input to C and hence C will behave like OR operator. So C will be like A or B. Okay. So if both of them are not there, that means there is no input to C and therefore the output is going to be 0, right? Or output is not going to be activated. And if A is activated and B is not, then also there are two inputs to C. Therefore, the output is going to be 1. If B is activated and A is not, still there are two inputs to C and you still get 1. So this way, just by a simple mechanism that this C gets activated when minimum of two are associated with it. Minimum at least two inputs are available. Okay, so we can create all kinds of structures to mimic all kinds of functions. Now, let's say the not operator we had designed it separately. Okay, so here we can also design things like A and not B in the same fashion, the way we have done earlier. Okay, so here we are saying not of B, so we are saying A and not B. Okay, so let's say B is on. So here this is a reverse. Let's say we have put a reverse signal here. So if B is on, therefore this will be 0. This won't go ahead, and hence there will be two inputs to it to this. Okay, there will be two inputs to this from A, and if B is on, then this will be off, and so on. So essentially, we'll be able to create these kind of structures using the ANN. Okay, but there are faults to it. There are faults to the simple primitive model. Those faults we are going to cover now. So this model, this model of artificial neural network was very primitive. Okay, in this, even though it was clear that yes, we need to assemble the various neurons together, but here we were just taking into account number of connections, not the intensity of individual connection. Okay, and therefore there was always it could not predict much. It could not move ahead much. So in 1957, Frank Rosenblatt gave a very interesting idea. Okay, so it is called, basically he gave the idea of LTU, linear threshold unit. Okay, this is again this is again a very simple model, just like linear regression. This is this way. It's basically very similar to linear, or you can say logistic regression. Okay, so and let's go over this model, and because this is what we will combine with others and will create the next model. This became the inspiration for the other models. The inputs and outputs are in this model. Inputs and outputs are, instead of being just the switches, on and off switches, here the inputs and outputs are numbers. So here x1, x2, x3 are inputs, and each input connection to this is our neuron, and all neuron does is whatever is the inputs, it multiplies them with certain weights, or you can say that these, while the input is coming to the neuron, those are multiplied with the weights, and neuron basically applies something called a step function. Okay, so the output is, first of all the incoming signals are summed up. Okay, incoming signals are basically multiplication of strength, which is the weight, multiplied with the input value, and summation of all such signals that are coming in. Okay, so the neuron receives this total summation of signal, and then all it does is it applies something called a step function. So this was the model, Perceptron model. We call it Perceptron model. It's again a very simple model. It's a Perceptron model as we can create, right? So this was a Perceptron model whereby all the input values are numbers instead of only the booleans. So it was a weighted sum of all the input values. Now, so the only difference is when it's giving output, instead of giving numeric value, it's giving something like a step function. Just like in value, when the value was lesser than something, it suddenly went to 0. If value was here, if value is above certain value, it is 1. If it is value is below certain value, it's 0. So there are many steps functions that have been proposed. One of them is Heaviside. Heaviside is nothing but if Z is lesser than 0, the outcome is 0. If the Z is greater than 0 or equal to 0, then the value is 1. So it's exactly like this. If the value is lesser than 0, if the value is lesser than 0, then outcome is also 0. If the value is greater than 0, if you think of this way as x, this way as y, and you look at this, it's basically saying that if x is greater than 0 or equal to 0, then the value of y is how much? 1. Okay, so that's basically the step function. So all in case of perceptron model, what perceptron does is all the incoming values it sums up, and how it sums up by multiplying weights to the input value, and then applies something called a step function. Okay, so there were sometimes another kind of step function used called sign. The sign gives either of the three values. The sign gives either of the three values, -1, 0, and +1. Okay, so this was perceptron model. So you can look at it this way. So a single LTU can be used for simple linear binary classification. It computes a linear combination of inputs, and if the result exceeds a threshold, it outputs the positive class or else outputs the negative class, just like logical regression classifier or linear SVM. So this is very simple. For all of the input values, it multiplies with certain weights, then sum it up. If the summation is greater than 0, the outcome is 1. If summation is less than 0, outcome is 0. Okay, so that's how the perceptron model works. So for so we could use the perceptron model to do the iris flowers classification. We could use that, and I'll show you that it actually works well. Okay, so we could use a single LTU to classify iris flowers based on the petal length and width, and adding an extra bias feature x naught equals to 1, it will basically give us the right values. Okay, so let me just show you. You can open the second notebook, right? In the same folder, in the deep learning folder, you will notice introduction to artificial neural networks. There, first section, this section that you see in the beginning, this is common for all. This is common for all. So basically, these are utility functions that we have created. Okay, so that we can reuse those. Okay, now the second here, this is the example. So here is this is the perceptron model example. Here we are trying to solve the iris problem. So you can see here, first we are importing data sets, specifically the load iris function we are getting from data sets. Then we are saying we are importing a class called Perceptron. Then using this method load iris, we are loading the iris dataset. Okay, so if you are interested, you can actually generally break it down and take a look at how does the data looks like before doing the rest of the steps. Okay, so this is how the iris dataset looks like. Okay, this is how the iris dataset looks like. Okay, you have the size of the petal and the sepal. Okay, the length and the width, and there are target variables, as in these are the features and these are the target, as in which flower it is. Okay, again, what is that we're trying to solve? Given the sizes of sepal and petal, we are trying to predict the various flower types, specifically the iris flower types. There are setosa, versicolor, and virginica. Those are the ones we are trying to figure out based on the sizes of sepal and petal. Okay, so here let's just say, okay, so that's what we're trying to do. Now, let's say for time being, we are just solving it based on petal length and petal width. Okay, and also we just want to check which flower it is. So we are saying whether it's setosa or not. Okay, so we are just say comparing the value with setosa, because setosa means the 0 value. So if the value is 0, that means it's setosa. If it is not, it could be either versicolor or it could be virginica. So we are saying y equals iris.target equals 0. That means that if it is 0, that means the value will become 1. Otherwise, if it is 1 or 2, the value of y will become 0. So for everything other than setosa, it will become 0, otherwise it will become 1. Okay, so capital X is going to be just the first, just second and third, which is I think these two, right? And you can see petal length and petal width, those are the last two columns. So these are the two columns that we are going to retain. And yes, all right, so we have capital X and small y, and then using perceptron model, okay, we are basically initializing the perceptron. Then we are saying fit perceptron dot fit, passing x and y, and then once we have trained it, this is where the training is happening. We are saying perceptron dot fit and passing x and y, and afterwards we are starting to predict. Okay, so we can take a look at this. So here you can see that it has done the prediction. So let me just take a look and show you. So you can see the predicted value is y for 2 and 0.5. 2 and 0.5. Okay, 2 and 0.5, how much is it? So let's say I can't figure out. Suddenly it's jumping. Okay, so it's difficult to see it manually, but yeah. So you can see that using the Perceptron class is available as part of the scikit-learn default model. Okay, and okay, so Perceptron class is available as part of the default model, default scikit-learn packages, and we are using that one. All right, is it clear what we are trying to do here? And the various coefficients, intercept, everything remains same. So this is basically just like linear regression. We have used the Perceptron. Okay. Bintao, James, Pavan, Shahrukh, Pratik, and Shiva. Okay, so we just used the Perceptron model. So Perceptron model does work, but it is very, very simplistic. We'll see that it doesn't work for many other use cases. So the linear threshold unit, for example, we could use a single LTU to classify iris flowers just the way we did. It internally, the function that we use, the fit method, it internally used the extra bias feature by itself. So Perceptron is simply composed of a single layer of LTUs. Okay, this Perceptron model essentially is basically composed of the linear threshold units. Okay, that's what our Perceptron model is. That's what is the model is, that it basically the okay. So okay, so Perceptron model is basically very simplified model in which there is one layer of neurons which are connected to the inputs, and we are getting the results. So input neurons just output whatever they're fed. So there is a concept of input neurons as well. So whenever we are creating the neural network, so whatever input we have, we create them as input neurons. Okay. So they basically output whatever they are fed. An extra bias feature is generally added here in case of Perceptron model, and this bias feature is typically represented using a special type of neuron called bias neuron, which just outputs 1 all the time. Okay, so this diagram, you can see that this is far more clearer, that all we are doing is, okay, all we're doing is we're trying to just say, initially, we would be assuming W1, W2, W3, W4, W5, and then multiplying that with X1. Then whatever is the output, if the output is not great, we change these W1, W2, W3 using the standard mechanism, whatever we learned in case of linear regression, and so on. So it is very much, the perceptron model is essentially the linear regression model. Okay. So now, so here basically the person in this model, you can see that um, we could have we could represent it like this. So we could in here we have two inputs and three outputs. This perceptron can classify instances simultaneously into three different binary classifier. So we can build the multi-output classifier. Okay, in the exactly same way. In the exactly same way, just like we did earlier while we were classifying things. So we created multiple, what was that? Versus all kind of one versus all kind of mechanism. So let's say this is for setosa, this is for versicolor, that is for virginica, right? So if so what we can do is we can basically here it is setosa versus versicolor. This is, sorry, setosa versus others. This is the what was the second flower's name? So this was the, okay, versicolor, setosa, and virginica. Okay, so these are, right, these are, okay. So basically the same thing can be further extended to give multi outputs. The same thing could be extended to give multi output. So let's say, okay, so basically all we are doing is here we're giving the weightages to every edge or every connection, and then we're multiplying with that weight to the input, and then we are computing this summation of all of that, and then we are applying a step function. Okay, that's what we are doing here. All right, just like we did, exactly like what we did for logistic regression. A question from Inta is why we need output one by bias. So why do we need this? Just like in linear regression, let's say, I'll tell you. So it's an important idea. And let's say we are trying to, okay, how do you, okay, say we are trying to do right, any regression, so any kind of output. When we say, let's say my salary is proportional to my number of years of experience, what does it mean? It means that my salary is equal to some multiplier of number of years, correct, plus some bias, right? If my years of experience is 0, that doesn't mean that my salary will be 0. Maybe I'll get some stipend, right? So that's the bias. Okay. If we don't put a bias, if we don't put the bias, then if the input is 0, the output will also be 0. That's why there's always this need of putting the bias. Okay. So we put the input as 1, and therefore the weight of the bias is going to make it that way. The B will be basically the weight of the edge. Is this figure clear? So it's a perceptron model. In the perceptron model, all we do is for every input we create just pass-through nodes. These are just symbolic nodes, and we call them symbolic neurons or pass-through neurons. And for every input, it basically just send the data further. In the output layer, all of the input neurons are connected like this, and so on. So, and all of these units are similar. All they are doing is they are basically outputting 0 or 1 based on the weightages of the edges. These weights or these weights is what we need to find. Okay, these weights is what we need to find as part of training the model. Okay. So question is, why need a output 1 by a bias? Okay, so yes. So here this is clear now. Second question is, why need a output value of 1 here? So this basically, there will be a weight to it, right? Weight, there will be, so let's say this is W1, this is W2, this is bias. So the output will be, let me just take a screenshot of this one. Okay, so where did it go? Okay, so here, let's say this is X1, this is X2, and here we have put the bias, right? So if you see, this is going to be, let's say, weight B, this is W1, this is W2, right? So here, the value is going to be W1 X1 plus W2 X2 plus B, right? And then we apply the step function on top of it. In the same way, we'll have different weights here. This is, let's say, B1. So we'll just put B1 here. Okay. There'll be B2 and there'll be B3. So like that. Is it clear? No. So all we're trying to do is we are trying to just understand what does it mean by perceptron model. Perceptron is nothing but very similar to linear regression, whereby we are basically multiplying certain weights to each input and then adding a bias, and then we are trying to find out those weights as part of the training. Okay, so that, and then we are applying a step function at the end. Okay, so in order to train the perceptron, we generally follow something called Hebb's rule. In his book called The Organization of Behavior, published in 1949, Donald Hebb suggested that when a biological neuron often triggers another neuron, a connection between these two becomes stronger. Okay, and connection between these two becomes stronger. So in simple words, it became a catchy phrase that saying cells that fire together wire together. Okay, so that was the idea. So a question from Binta is how to choose a value of bias. So here the bias neuron, the value is always 1. This is always 1. Okay, and this B value is what the multiplier to this one is what is part of training. Okay, this is what is part of training. So we will learn that as we go ahead. Okay, great. So we generally followed the Hebb's rule in order to train a perceptron. Okay, the perceptrons are trained using a variant of this rule that takes into account the error made by the neuron, made by the network. It does not reinforce the connection that led to the wrong output. Okay, so what's happening here? So when we are having the perceptron model like this one, right, this one, so what's actually happening is it is going to enforce the connections. Connections means these weights. It's going to enforce the weights if the one that is leading to the result is giving good results. That was Hebb's rule. The one that's not leading to good results, those connections will become lighter, or the weights become smaller. So it does not reinforce the connections that led to the wrong output. The perceptron is fed one training instance at a time. For each instance, it makes the predictions. And for every output neuron, that produced a wrong prediction, it reinforces the connection weights from the input that have contributed to the correct prediction. Okay, so this is what the perceptron training looked like. This is exactly like the gradient descent. This is exactly like gradient descent. Then the weights, the next time weights are going to be equal to the weights previously plus eta, which is the learning curve, multiplied by the difference between actual versus predicted, multiplied with the actual value. Okay, this is exactly like gradient descent learning, in which we were computing thetas. Here we are computing w's. Wij means the weight between ith neuron and jth neuron. This could be right. So this is basically the perceptron learning rule. Okay, so at every step, this is what is computed. At every step, the next weights are computed using this. All right. Now, okay, a question from Binta is how to choose the value of bias, 1 or 2, with the value of input, the input neuron, which is designated for the bias, is called 1. How do we know our prediction is wrong if there is no actual value available? How do we know our prediction is wrong if there is no actual value available? The weights are there. So B is the weight. So going back here. So the output, as we said, this is the output, okay? W1 into X1 is the input, W2 and X2 and B1, right? So the X1 and X2 are the input. W1, W2, and W3 need to be figured out based on the data. So every time we will, in the beginning, what we will do is, this is our output. In the beginning, we will assume certain values of W's. We will assume certain value of W1, W2, and B. And then in the next round, what we will do is we will compute the predicted versus so okay, let me take a step back. So imagine that this is our output, W1 into X1 plus W2 into X2 plus B1. B1 is the edge, okay, for the neuron whose value is only 1, right? This is the bias, okay? So we generally, the input value for the bias, we put it as 1. It's an extra neuron, just like we put one column in every linear regression. So this is our output. So we need to figure out all these three values, W1, W2, and B1, all these three values for this particular classification, right? So initially we'll take the random values for W1, W2, B1, and then we'll apply this kind of formula to compute the next values. This, the initial weight plus eta multiplied by this value. So initially we'll compute this y. This is our y, okay, and then we'll compute the y minus the y cap minus y, which is the difference between actual versus predicted. So right now the predicted is based on the weight, which is based on the random weights, and then once we get the error, we'll change the weights of each one, and then basically do the recomputation and again compute the error, how much error are we getting, and based on the error we readjust the weights, and that's what we keep on repeating again and again, and we call it the we call that as so we keep on repeating again and again, and we call that training. Okay, this is perceptron training. Question from Binta is, how do we know our prediction output is wrong if there is no actual value available? There is actual value available, right? Here, the output, we know the actual value. Okay, so initially there's going to be the actual value. So we are feeding this value x1, x2, and then comparing it against the actual value. If that is whatever is the difference, based on the difference, we are changing the value of weights, and that's how the training is happening. Okay, the actual value is available here. Okay, okay, was able to answer with the, so the way we just showed you here, if you take a look at this particular example, in this example, right? So capital X is the input, Y is the expected output, right? Y is the expected output, and we are saying perceptron dot fit, and we are passing X and Y. Okay, so here what it's going to do is it's going to first assume the weight values with random numbers. Then it will basically, for every record in X, it's going to compute Y, compare with this Y, and then based on the difference between the predicted versus actual Y, it is going to reinforce the various weights. Okay. All right. How do we know our prediction is wrong? Okay. If there is no an actual value, there is actual value available, right? Question from Bintao is that how do we know our prediction is wrong if there is no an actual value target? There is target value available here. Okay, just like we did earlier. Okay, let me take a step back. I hope I'm not off the track. So here, let's say this is our actual value available, right? For x1, x2. Now our predicted value is this. So we assume w1, w2, and b1. Then we compute the difference between actual and this, and then we do that. All right. Then based on this formula, as in we subtract the actual versus the we subtract the predicted minus actual, multiply with the input, and then we multiply it with some learning rate, then we add it to the previous W. Okay, so yes, of course we must have a target outputs. Okay, this is the Perceptron model and most of what we are learning is part of the supervised learning. So we have the training data available. Okay, we have the training data available. So all we are doing is we're computing the outcome, comparing with the actual, and then changing the weights, and then again trying the same thing. So that's what is happening as part of the Perceptron training. Yes, this is supervised learning. That's right. Thank you for the question. Okay, so is it making sense to you, Shiva, Pratik, Pavan, Shahrukh, James, and Binta? So we are training the perceptron, and it's extremely similar to what we learned as part of the gradient descent and in the linear regression. Okay, so that's what we are trying to do. So we are basically computing the weights based on the previous, whether previously we were successful or not successful. Okay, that's how it is doing. So the descent boundary question from Pratik is, how do we update the bias in the same way? A question from Pratik is that since there's a variable called bias as well here, the bias here, and do we update the bias? Yes, we do update the bias in the similar way. Okay, and even though it doesn't say weights, so you can always assume this to be one of the weights. Okay, you can always assume this to be one of the weights, and you can consider it exactly like you consider the weights. Okay, that's why in this model the This basically, this behaves exactly like normal neuron, just that its value always is 1. So the weight computation for this one as well is same as the rest of the neurons. Okay, great, great. All right, very good set of questions from all of you. Okay, so keep asking questions. That's the only way to learn. Okay. All right, so this boundary for each output neuron is linear. So perceptron are incapable of learning complex patterns. So exactly the problem that we faced in case of linear regression, the same problem is here as well. We the The perceptron model is extremely simple. It's exactly like linear regression. Therefore, the training instances are also linearly separable. And Rosenblatt demonstrated that this algorithm would converge to a solution in case of linear cases. And this is called perceptron convergence theorem. Okay, here we have basically tried to demonstrate how to run that, right? So contrary to logistic regression classifiers, perceptrons do not output a probability. It does not give out the probability. It says yes or no. They just make predictions based on a hard threshold, right? Like hard voting. So basically, it doesn't give you the probability. Instead, it gives you 0 or 1. Therefore, they are not they are not preferable to even logistic regression. So, so between logistic regression and perceptron, people prefer the logistic regression because logistic regression, you get the probabilities. Also, the perceptron model was incapable of solving a slightly more complex problem, such as XOR. The XOR classification problem, it was not able to solve. Right, so that's why there was a need of the newer model. It's called multi-layer perceptron model, and this multi-layer perceptron model is something that's actually that's actually is quite useful, and this is what became the neural network as we perceive today. Say for example, with MLP, multi-layer perceptron, it turns out that there were some limitations of the previous one. So the MLP solves that problem. Imagine that you have two input variables, A and B. Okay, those are your input variables. What is XOR? XOR is nothing but if two values are equal, XOR is A XOR B, meaning if both A and B are equal, then the outcome is 0. If both A and B are different, then outcome is 1. That is XOR gate. So since perceptron model wasn't able to solve it, therefore the multi-layer perceptron was created, and that's what is used as of even today. A variation of MLP is what we learned today. A question from Binta is, what are the data types of learning rates and weights? Learning rate and weights, those are float actually. All of those are float. Okay. All right. Good question. Moving ahead. They are not integers, they are float. Good. All right. And now, so the perceptron was not able to solve even slightly harder problems, and therefore there was a need of a newer model, and that model is called multi-layer perceptron. If you connect multi-layer of neurons, then you can actually get really good result. For example, let's say we have, let's say, this multi-layer model. It has one input layer. This is input neuron. They don't do anything. They just feed the data. And this is bias one. And then this one sums up. does some operation, this one does some operation, and this one does some operation. So you can see that the input of one layer of neurons is being fed to another neuron. This is called multi-layer. So let's take a look. Let's take a look at this XY. Imagine that we have this. Okay. Imagine that. Okay. Right. Imagine that we have this kind of a model. Zoom it out. Okay. Imagine that we have two layer perceptron. It has this, and this. These are three neurons, and these are one input layer. So let's test it out for XOR. Imagine we have put 0 for x1, 0 for x2. Okay. And also it gives either 0 or 1 based on whether the value is negative or positive. If negative, then it gives 0. If positive, it gives 1. So let's take a look at it. So let's say x1 is 0, x2 is 0. So, and here the weight is +1 for both of these. So this becomes 0, 0. And what is the input coming from here? It is minus 0.5, right? Therefore, since this is lesser than 0, it becomes 0. Okay. So let me put for 0 and 1 similarly. Let's say here this is 1. So here the calculation will be x1 plus x2, x1 into weight and x2 into weight plus b into 1. This is what the calculation be. And if this value is lesser than 0, the outcome is going to be 0. If it is greater than 0, the outcome is going to be 1. Okay, so let's take a look. If x1 is 1 and x2 is 0, so here the outcome is going to be 1 into 1. This is the weight. Okay, so 1 into 1, right? So okay, so the outcome is going to be how much? 1 into 1 plus 0 into 1 plus here 1 into minus of 1.5. Correct? This is how much? Anybody? This is how much? This is 1 plus 0 minus 1.5. So it's minus 0.5. Minus 0.5 is lesser than 0. Therefore, this is going to be 0. Correct? In the similar way, if you do here, so 1 into 1 plus 0 into 1 plus plus minus 0.5. So this is again minus 0.5. It's not okay. Let me put it this other again. So it's going to be 1 into 1 plus 0, 0 into 1 minus 0.5. Correct? So we are doing is taking the input, multiplying with the weight of edges. Here the weight of both the edges is 1, right? So here 1 into 1, 0 into 1, and then 1 into minus 0.5. So this is how much? This is 0, and this is positive 0.5. And if something is positive, we mark it as 1. Okay, so here we have 0 and 1. Now again, this is going to be multiplied with minus 1, this is going to be multiplied with plus 1, and then summed up with 0.5. So it's going to be positive 0.5, which means if anything is greater than 0, we're marking it as 1. Okay, so you can see that if 1 and 0, we're getting 1. Similarly, for 0 and 1, we will also get the same result, right? And if both of them are 1, yes, then what would happen? If both of them are 1, then this is going to be 1, right? And right, I think you can actually do a better job with an Excel sheet instead of this one. and that way you can always get better results. Okay, so yeah, let me just see if I can do it quickly using Excel sheet. Okay, and yeah, that'll be a good exercise. All right, let me see if we could do quickly. Ouch. Oh, you can't insert an image. Okay. All right. So let's say this column is x1, this column is x2. Okay. So this is x1, x2, and let's say we call them, say, L1 and L2, and then we call it output. Okay. So if x1 is 1, 1, right? L1, let's say this one is equal to how much? First multiplied with 1 plus second multiplied with 1 plus bias subtracted by 1.5, right? In the similar way, we have the second one. Second one again, it is A1 plus this, and this is the second one, right? And here again, we'll have to do the max of right, 0 and 1 and so on. So okay, that I have to figure it out. So you can always figure it out from the, so let's say out of Z1, Z2, and okay. So this one is, if this is positive, we put it 1. If this is positive, we put 1. And the outcome is again this multiplied with -1 plus this multiplied with 1 and minus 0.5, like that. If this is 0, we put it here 0. Okay. So if both are 1, the outcome is 0. So that way we can compute. These are basically, these values are, we have done the rounding off by ourselves. Similarly, as in we are doing the step function manually instead of using the Excel sheet. So similarly, we could do for 1 and 0, right? So we could do 1 and 0 here. So this is negative, so we put 0 here. And this is positive, we put it. Okay. So the outcome is 0.5, therefore 1. So you can see that we are able to do the computation by ourselves. All right. So in the same way, we can do the computation and we will get the correct results. So what we are trying to demonstrate, yeah, I think we can try using ceiling and floor. Yeah, that's a good idea, Shiva. All right. So So what I want to demonstrate to you is that if we take the simple perceptron model and we put multi-layers to it, even if we have simply two levels, the it it becomes capable of solving complex problems. And XOR is considered as kind of a complex problem. Okay, so it was able to solve um, a problem like XOR. Instead of doing the prediction using the given data, here we are doing the prediction which were supposed to be XOR based. So here we are basically solving those problems. We are able to solve the XOR kind of a problem. Okay, so MLP is composed of one layer, one input layer, we call that input layer, and one or more layers of LTUs called hidden layers. Okay, and one final layer of LTU called output layer. Okay, so we have output layer, we have input layer. Output layer is basically not doing anything other than printing the results, and the input layer we are feeding the data, and in middle layers we are doing the two sets of computation, one's here, other here. Okay, so we're doing the computations twice, two times. Okay, so every layer except the output layer includes a bias neuron, okay, which has different weightages just like normal neurons have, and is fully connected to the next layer. Okay, so in deep neural network, when ANN when ANN has two or more hidden layers, if this layer is more than one, we call it deep neural networks. Okay, so for many years, researchers struggled to find a way to train MLPs without success. Okay, in 1986, D.E. Rumelhart published a groundbreaking article introducing the idea called backpropagation training algorithm. Today, we would describe it as gradient descent using reverse mode autodiff. Okay, so basically, even though it was considered that yes, the neural networks will be able to solve the problems, but the problem was at that point of time that how do we train it? How do we find the values of weights, W1, W2, the value of bias, and so on. So that was the biggest challenge, because as the layers increased, training a neural network became furthermore harder. The total number of permutations became really high. So how many total number of variables are we trying to find in this layer? Anybody? How many variables we are trying to find? Okay, just like we solve equation for x and y, how many such variables are there in this? Anybody? How many such variables are there? That's right. It is 27 such variables, because every edge that you see here is basically representing a weightage that is being multiplied. So, these, how many total number of edges are there? 5 into 3, which is 15, plus 5 into, right? Sorry, 3 into 4, which is 12. 12 plus 15 is 27. So you can see that total number of edges is what we represent as weights, and every edge has got the weight, in other words. So we are going to find 27 edges even in a very simple 27 variables even in a very simple network, simple neural network. So therefore it was really difficult problem to find the various weights, and this is where the backpropagation training algorithm comes into play. Okay, so what is backpropagation? For every training instance, the algorithm feeds data to the network. Okay, so for every training algorithm, what we do is we feed the data here. Okay, and then the it assumes certain value of weights of every edge and compute the output of every neuron in each consecutive layer. So first, we are computing the output, right? So we have assumed the weights of every edge, and we are computing the output. And again, once we have done here, we have assumed some value of it, and we are computing the output. This is called as forward pass. So first step is that we compute the output by assuming the random values. The second one is the second step is called backpropagation. What we do is we find the error in the output. We compare the output with the actual value and then say that, okay, this is the degree to which we have been mistaken. This is the error that we have made, right? And once we know that, we go backwards from here and distribute this error, saying that, hey, this I got this much overall error, and and you are responsible for this part of the error, you are responsible for this part of the error, and you are responsible for this part of the error. Okay, you are responsible for this part of the error, and that's how the error backpropagates. And in order to do further fixing of the error, again, in order to fix the weights of the edges, we further propagate the error. Okay, so basically, in the first pass, what we do is, given the weights, we first find the output error. We find the difference between the desired output and the actual output of the network. Then we compute how much each neuron in last hidden layer contributed to each output neuron's error. It then proceeds to measure how much of those error contributions came from each of the neurons in the previous layer, and so on until the algorithm reaches the input layer. So the last step in the backpropagation algorithm is a gradient descent step on all the connection weights of the network using the error gradients measured earlier. Okay, so in the backpropagation, the last step is basically, okay, so using gradient descent, it basically computes the weights in the network using error gradients measured earlier. Okay, so the reverse pass efficiently measures the error gradients across all the connection weights in the network by propagating the error gradient descent backwards in the network, and hence the name is backpropagation. Okay, so let me summarize it again. So in forward pass, for each of the training instances, the propagation algorithm first makes the predictions, measures the error, and then goes through it goes through each layer in the reverse to measure the error contribution from each connection. Okay, then it goes through that, and then finally it slightly tweaks the connection weights to reduce the error, and then it basically makes changes to the weights and does the forward pass again. So these are the four phases of the backpropagation algorithm. Okay, so it's a little complex, but let me try to explain. Okay, I'll try to explain it in very further more simpler words. Okay, though it's completely okay to not know backpropagation. Okay, Okay, so in the first pass, what it is doing is, let's say it has assumed some value, right? So it is computing x into w here, and again it's computing. Let's say these are called x1s, right? That's called x1s. So again, it's computing x1 into w1s. Let's say these are called w1s, right? So the output is going to be w1 and x. Okay, it will be x into w, but don't worry about that, into x1. So w1 into x1. So all it is doing is first is computing the output, and once the output is computed, we know the error. The error is equals to the predicted minus actual. Okay, so we get the error as predicted minus actual, and this error propagates backwards. Okay, so we figure out that, okay, this error is because of this particular node. And how does it do that? What does it do is, it knows that what is the error, right? It knows what is the error, and it also knows what is the rate of change of error because of a particular edge. So it knows this part, and based on that, it figures out that if this error changes at certain pace, if its node's value changes at certain pace, what would be the impact on this error, right? So it knows that how is error related to this node's value related to the previous node, and it also knows that if there is X amount of change in here, how much amount of change is going to be here. So using this knowledge, it basically propagates the error backwards, and it keeps on going. And here, while it is doing the propagation, it would compute the new values of this edge, or new value of this weight, and then it'll do the forward pass again to compute the output value, and does the compare again, and then after comparison, it goes back and figures out who is the culprit, or which edges are the culprit, or which weights need to be tweaked. A question from Bintao is, does error backpropagate with the same weights? Um, so yes, it basically figures out that part using something called reverse differentiation. It figures out that which weights are impacting the most. It figures out that part, and then changes the error, changes the various weights. Okay, do I make sense? So error does not backpropagate with the same weights. Instead, it is in the proportional of the weights. It is a function of the weights. Okay. So I'll put it this way. What is an error, right? Error is equal to W1 X1 plus W2 X2, right? Plus maybe say W3, maybe plus, let's say, I think I'll do using this. This is better. Yeah, this is better. Okay. So let's say, let me put here, say W, we'll call it W1. Actually, it becomes just too many variables, W2 and W3. Okay. So we get the error equals to how much? Or let's say these values are there. Let's say we call it x3 plus 36 x7, and this is x8, this is x9, right? So at this point of time, we know that the value of all of these, and x into w1, right? x8 into w2 plus x9 into w3, correct? So that's the value of error. Now, x7, 8, 9 is kind of, let's assume them to be constant. Okay. Now at this point of time, it computes that the rate of change of error is with respect to each of these values, with respect to x7, with respect to rate of change of E, with respect to the weights. How much is that? So it computes these values, and then based on this, it computes that which one is more responsible for the error. Who is more responsible? Here, I forgot one part. Here, this is y actual. Okay, this is y actual. So at this point of time, it knows the error, how much we got the error at this point of time. Once it has gone forward by assuming these values of weights, it has computed the error. And at this point of time, it knows how error depends on each and all of these. Correct? So using the reverse differentiation, we call it reverse differentiation, it figures out that the dependency between this and this is how much. And based on that, it basically decreases or increases the weights in that proportion. Okay, if this output is a function of this one more, then it basically increases the weights here. Okay, and it'll keep on going backwards to compute the other weights. Okay, a question from Bintao is, does error backpropagate with the same previous weights? No. Second question is, how to adjust the weights manually or by experience? No, we don't do adjust weights. We basically start with random weights, and then backpropagation basically does the job for us. Okay, so so even though there is a maths involved, but I think we can understand this in this way, that in the forward pass, for each training instance, the backpropagation algorithm first makes the predictions. So here at this point of time, let's say in the beginning when we start, we don't know any of the value of edges. We know these input values and we know the expected output, correct? We know these input values, right? And we know the expected output, right? So what we do is we basically assume the value of edges. Based on that, we compute these values. Then we again assume the value of edges. We again assume the value of edges. And then we again do the computation. And then we will get some predicted value here. Okay, we get the predicted value. Okay, this is the predicted value, and we subtract that from actual. We subtract that from actual. Okay, so that is the error. Now we will start propagating the error backwards now after this. Okay, so we did the prediction, measured the error, so we are here at this point. Next is we go through each layer in reverse to measure the error contribution from each connection. We compute the error contribution from each of the node. And finally, we'll slightly tweak the connection weights to reduce the error. Okay, so now we know the contribution ratio from each of the nodes, and hence we know how much weight to give to the edge. So we'll keep on tweaking the weights, and we'll keep on we'll compute the error, we'll find the responsible nodes which are due to error, and then we'll reduce their weights. And if the everything's good within the tolerant limit, we will print the results. Okay, does it make sense to you? So all we do is we compute the value of output, and we find what is which ones are responsible, and accordingly the value of the layers we tweak, and then we start tweaking the W's, and until we get the reasonable values. All right, so that's pretty much for today. Bindao, James, Shahrukh, Pawan, Pratik, Shiva, was this example clear, the idea of backpropagation, or you would need one more pass? I'm also going to do forward pass, backward pass. All right. So you want me to walk you through the same again? All right. Great, great. I look forward to see you next Saturday, because tomorrow being Easter, we are keeping a holiday. Okay. All right. So you must have got the email from our site. So some of the students wanted a holiday tomorrow, so we thought of keep the holiday. All right. So tomorrow is no class. Next class will be on. Next class is going to be on the next Saturday, 7 days from now. Shiva's question is, do we need to know the maths behind this? Honestly, you don't. Honestly, you don't, because even without maths, we have expressed the same thing theoretically. You must have got it. But if you are curious to know maths, let me know. I can schedule one separate session and we can go over the maths. All right. We have class today for the Spark, yes. Okay. Book question from Pavan is, any book on ANN? I'll share the book. Okay. All right. The artificial neural network and deep learning.com. The name of the URL is bigger, so that one is actually quite useful. Okay, so you can take a look at that one. All right. So, all right, in the next session, we are going to basically train our first neural network using the MNIST, and I think that'll give you the better picture. Okay, theoretical parts are generally a little bit boring, and I think when you do the hands-on, you will get more picture. All right, I look forward to see you next Sunday, and thank you very much. Thank you, Bintao. Thank you, James. Thank you, Shahrukh. Thank you, Pratik. Thank you, Shiva. Sure, I'll send it to you. Okay, so okay, so I think, yeah, this is the one. It's actually extremely simple book. You should take a look at it. Thank you, everyone. Have a good day. Bye-bye.